In a world so dominated by networking and the internet, there's a high need for clocks and computers to remain synced. How can two computers on opposite sides of the globe sync their clocks with a fraction of a second precision? I'm Brian Stamp, and let's talk Network Time Protocol. So what is Network Time Protocol? Well, NTP is an application layer protocol for synchronizing clocks between computer systems through Coordinated Universal Time, or UTC. Sort of. NTP can retain accuracy within 10 milliseconds over the public internet, or better than 1 millisecond in local area networks under ideal conditions. NTP is implementable as both a server-client model and a peer-to-peer model. However, this presentation will only focus on the former. NTP was designed by this chap, David L. Mills. The first version, NTP v0, was implemented in 1985, making NTP one of the oldest protocols still in use today. Since then, several revisions have been made to improve efficiency and security. The current version is NTP v4. Alright, so how does it work? Before we get too far into that, we need to discuss stratums. NTP servers are structured into a hierarchical system, where each level is called stratum. Starting at the top, we have stratum 0. These are high-precision timekeeping devices, such as atomic clocks and GPSs. Note these are not servers. An NTP server cannot advertise itself as a stratum 0 server. Moving down a layer, we have stratum 1 servers. These are computers whose system time is synced within a few milliseconds of their stratum 0 devices. These servers may also pair with other stratum 1 servers to provide backups and sanity check their measurements. Note in this diagram, yellow arrows indicate a direct connection, whereas red arrows indicate a connection with the network. Stratum 1 servers are also referred to as primary servers. Going to another level, we have Stratum 2 servers. Stratum 2 servers are synced to Stratum 1 servers over a network. They will often query multiple servers, as well as peer with other Stratum 2 servers to provide more stable time measurements. From here, the pattern continues, with the Stratum N server syncing with Stratum N-1 server. The maximum Stratum number is 15. Note the Stratum number indicates the server's distance from the original time source. It's not necessarily an indication of its accuracy. In fact, it's common to find a Stratum 3 server that's more accurate than a Stratum 2 server. The biggest contributor to decreased accuracy is network latency, not the number of hops. Now let's take a look at the NTP server-client relationship. NTP servers are stateless, meaning they do not store information between requests. They use UDP as their transmit layer protocol. A typical NTP client will pull one or more NTP servers. A request packet may look something like this. A lot of fields to be sure, including a field for the stratum number we just talked about. But specifically, pay close attention to the origin, receive, and transmit timestamps. These are populated during important times in the request lifecycle, those being when the client first sends the packet, when the server first receives the packet, and when the server retransmits the packet back to the client. The client will also record when it receives the packet back from the server. So we've made a request to the server and gotten our packet back. What do we do now? The short answer is math. The longer answer is as follows. Consider the diagram of formulas. T0 to T3 represent our timestamps. The client will use these formulas to calculate the time offset between the two clocks, theta, and the round-trip delay, delta. These values will be calculated from all queried servers. Next, they are passed through filters and are subjected to statistical analysis. The goal is to determine outliers and choose the best fit results. These results are then used to adjust the clock gradually to reduce the offset. Concerning security, it can easily be seen how NTP is vulnerable to denial of service attacks. However, more interesting is how NTP can be exploited using man-in-the-middle attacks. If packets are spoofed, attackers can gradually move a client's clock, which can allow for other attacks based on cryptographic key expiration. Although this can be avoided by signing packets, the overhead can be impractical on busy servers. Several implementations of NTP have existed over the years. For example, all Windows versions since Windows 2000 have included Win32 Time, which can sync to Ntp Server. Another example is Simplified Network Time Protocol, which is a simplified version of NTP designed to be used with applications where the full NTP capability is not required. And that's NTP. To sum up the key takeaways, Network Time Protocol is an application layer protocol that can sync the clocks of computers over a network. NTP was designed by David L. Mills and was first implemented in 1985. The current version is NTP v4. NTP servers are organized into stratums, and an NTP client will pull multiple servers. The client will calculate the time offset and round-trip delay using the timestamps from the packets. These results will undergo statistical analysis, and the best candidates will be used to adjust the clock and reduce the offset. Of course, there's much more to NTP than what I can cover in 5 minutes, and if you are interested in it, I recommend more about it. It's a lot more interesting than you may think. Alright, that's it for me. Thanks for watching.